Yes. Hi everyone. It's a pleasure to give a talk at CPM. I will be talking about a new technique for approximating text-to-pattern distance. So in a text-to-pattern distance, I mean, this is a well-established problem already considered for, I think, at least more than 30 years. So, I mean, a standard setting in stringology, we are given a text and a pattern, and we want to compute something for every alignment of pattern to a text. So here we'll be interested in, so the most basic setting is just decide whether a pattern exactly matches with a text, but a more refined version is to decide whether it matches, or if it doesn't match, by how much it doesn't match. So a standard notion would be, for example, to count the number of mismatches. So that corresponds to computing a Hamming distance between those two. So in a more general setting, we want to just, for every alignment of pattern to a text, we want to compute a distance function between a corresponding slice or segment of a text and the pattern. So three distance functions I will be concentrating here on are Hamming distance. There's L1 distance, so a sum of absolute differences, and Euclidean distance, so a sum of squared differences. They all share a similar structure, which is just that it's a positional sum of some distance function between corresponding characters. And I think this is like an important thing to keep in mind. So here, for example, considering Hamming distance, we can just take our text and a pattern and just slide this window and count the number of mismatches. So here, for example, every character, I hope so, is different. And then we have distance 3, 3, distance 3, distance 3, and distance 1. And so basically, we are given as an input 2 words, and we want to output a linear size array of answers, of distances. So already in such a setting of just counting mismatches, Fisher and Patterson in 1974 gave for Boolean inputs. They observed that for Boolean inputs, it can be computed in linear time. I will discuss it a little bit more on the next slide. Then basically almost simultaneously, Abrahamson and Kosaraju generalized it to arbitrary size alphabets. So if, I mean, by arbitrary, I mean polynomial size alphabets. So this has a complexity of n square root of m. So this is not a linear time algorithm. This is n to the 3/2. Complexity times small, very slight logarithmic factor. And in fact, this complexity stands. So for such a general setting, we don't know whether it can be improved, or maybe it's a tight complexity. If you are feeling optimistic, then you can maybe believe that it can be improved. I know at least one person that thinks it can be improved. I think it will be a huge breakthrough, but maybe I'm also optimistic. But then, of course, we can relax the problem, because we all like linear time algorithms, and maybe we don't care about the exact number of mismatches, but just a magnitude. So you can get a linear time algorithm, so essentially 1 plus minus epsilon approximation, by a very simple application of random projections, and get a complexity of n over epsilon squared time. And then Kopelovitz and Porat, they improved it. So you might think that this epsilon squared coming from analysis of a variance of a process is tight, but in fact, being smarter about the projections, you can get n over epsilon time. And this is actual state of the art for the approximation version. And then if you are interested in in maybe counting exactly, but if you if the number of mismatches is too large, then you just want to say, oh, it's too much. Just by application of suffix trees or LCP queries, you can get n times k complexity. It's a simple exercise. It was improved, so you can generalize the n squared of m complexity to n squared of k. And so with Paweł Gabrychowski 2 years ago at iCalc, we improved the complexity to something that looks tight unless you get some computational complexity breakthroughs. So it's n plus kn over square root of m. It's a little bit weird complexity, but it actually makes sense in terms of trade-offs between n, m, and k. There were, as a side effect of a recent stock paper of Chan, Kociumaka, Kopolowicz, Porat, and Golan. Sorry for permuting the authors. This can be made tighter in terms of polylogarithmic factors. But there's one common theme behind all of those results is that, well, they all use some form of convolution for as a black box. And what do I mean by convolution? So I want to say that, well, already in the first results of Fisher and Patterson results for Boolean inputs, they observed that this problem essentially reduces to convolution. Just if you want to compute Hamming distances for Boolean inputs, this is two applications of convolutions. I will show it in a second. But convolution or polynomial multiplication or large integer multiplication, we all know it can be done in basically n log n, almost n log n time by FFT. If you don't want to reduce it to Fourier transform, there is a Tom Cook algorithm n2 to the square root of log n. It's a Karatsuba type approach. So the second one, so sorry, the FFT requires you actually embedding it in some field, either complex numbers or modulo p. The first one, so the Tom Cook algorithm is just basic arithmetics, but I mean it's suboptimal in terms of complexity on n. How does convolution plays here a role in a pattern matching? Well, if we have our two Boolean words and we think of them as polynomials, so I represent my Boolean input as a polynomial. I represent my pattern also as a polynomial, and I just multiply them. So if I just multiply them, if we observe that each coefficient of multiplication comes from combining many corresponding positions between P and Q, and it's essentially counting how many ones matched with ones on the pattern side and on the text side, but the pattern is just inverted. So to do the approach of Fisher and Patterson, you want to count ones against ones and zeros against zeros. So this is two multiplications of text and of inverted pattern, so of a reverse direction pattern. And that's basically the whole black box. That's how convolution is about counting of mismatches on a Boolean input. And this can be generalized and used in many various forms. And essentially, it has been used also for other norms, for L1 distances, the results of Lipski and Porat, or our result with Paweł, it used some form of convolution. Then 1 year later at CPM last year with Jan Studeny, we generalize it also to LP distances, and it also uses some form of convolution. So the convolution is all around the place. And the problem is, fine, yeah, it's a beautiful black box, but it's also a problem. It's somehow limiting. For example, if you are considering a streaming setting, you don't really have random access to the whole pattern and to the whole of text. So you cannot run a convolution in a streaming setting if you have a limited memory. If you have an online setting, so you're kind of changing the word on a go and updating and then querying, it's also problematic to run a convolution. So the question is this convolution here really necessary? Are we doomed to use it everywhere? And also, like, a small question is, well, convolution is really not a combinatorial primitive. It's hard for me to decide where there's this line dividing combinatorial and non-combinatorial primitives, but essentially just moving fingers through words and counting something is for sure combinatorial, and reducing it to complex numbers for me is not combinatorial, and there's like a full trade-off of combinatorial-ish algorithms here. So the situation here is that this year there was a paper at Stock where there was a very beautiful application of sampling and counting, and a full spectrum of results, improving many settings, streaming setting, offline setting. And it was not using convolution. It was just doing some sampling and counting. And it shows that if you don't use convolution, you can achieve something better. So you cannot just do sampling and counting if you want to go into different norms. Just for Hamming, it's okay, but for different norms, I mean, your answer will be large. So you cannot just count by one to your answer. So I wanted to apply a different framework. I wanted to apply a framework of sketching. So sketching is just this procedure where we have, imagine this communication complexity setting where we just have two words, two players, and they just encode their inputs into some short messages, some sketches. And then they send those sketches to a decoder. And decoder, just looking at the sketches, can compute a function between those two inputs. And a very useful tool is, like, if you just want to remember one thing from my talk, just remember about Johnson-Lindenstrauss lemma, not about whatever I was talking about. Johnson-Lindenstrauss is super useful and a beautiful thing. So imagine we have endpoints in a very large dimension, in a Euclidean space. And we are just not happy with this being such a large dimension. And we're just saying, okay, existentially, there exists a map into much smaller dimension that approximately preserves the distances between those points. You can go from dimension n to dimension log n over epsilon squared by introducing only 1 plus minus epsilon change in these distances. And in fact, such a random map is not only existential. I mean, such a linear map is not only existential, but it can be very easily constructed. In fact, choosing a random linear map is almost always good. So our takeaway message about Johnson-Lindenstrauss is that if you have a word, and we think of a word as just a long vector. If you have a long vector on dimension n, we can just apply a linear map and construct a very short vector, which will be a sketch of this word. And by result of Archaeoptas, this map can be just a random matrixed field uniformly at random with plus minus 1 coefficients. By results of Kane and Nelson, this map can be even made epsilon sparse by just preserving only a small number of elements in each column. And such a map, because it's linear, if I apply the same map to my word and you apply the same map to your word, and we compute the sketches, we can compute the sketch of a difference between our words by subtracting sketches from each other. And this map will preserve the second norm, the Euclidean norm. So the second norm of a sketch is a second norm of the original word. So we can effectively compute distances between words by applying the Johnson-Lindenstrauss. And it has been to a great success used in many streaming and non-streaming settings in a stringology right now. So maybe it will be easier for us if we just start with easier norm. So we start with Euclidean norm, not Hamming norm. So we start with L2 norm, and we sketch, we compute the projection of a pattern, and then for every window of a text, we also compute its sketch. So apply the same linear map to every substring, to every m subword of a text. So for first subword, for second subword, and for every other subword, we just compute the same linear map. The problem is that doing it naively results in a quadratic time computation. It will be n times m times time to evaluate the map. We can do it faster, but it's stupid because it will use convolution. We can apply the same linear map to every subword to compute the sketches. So we went all the way around to avoid convolution. And in the end, we use convolution. So it's maybe not the best approach, but it gives us some hope that it can be done. We just need to be smarter about it. So the actual idea that I had is not to use the full power of dimensionality reduction, not to reduce the dimension from some large n to some small d, but think of the Johnson-Lindenstrauss as a black box that allows you to reduce a dimension from 2d to d, just by a factor of 2. So I like to think of it as a small rectangular matrix that effectively takes two vectors of dimension d and produces as an output one vector of dimension d, and the second norm is preserved. So the square of length of x and y is preserved in the length of z, and it's a linear map. And this map can be evaluated in time effectively. If we remember that d is 1 over epsilon squared, this can be evaluated in time 1 over epsilon cube. And it preserves approximately the second norm of the vectors. And now, if we have a long word, what we do is we just chop it into pieces of length d, and then we apply those black boxes. So we have n over d chunks of length d, and then after a first layer of computation, we have half of those. After second layer, we have even less. So we just consecutively reduce the number of chunks by a factor of 2 until we end up with a single sketch at the end. And there are two properties. This sketch is a linear function from a previous layer, which was a linear function from a previous layer, which was a linear function from a previous layer, and so on. So effectively, it's still a linear map of the original input. It's just much more convoluted because it's an application of many layers of multiplication by matrices. And the second part is that it preserves the second norm of the input. And also, it can be evaluated in time n over epsilon. And why do we do this? Why do we made our life harder, not easier than originally? Because we can then now do the same, but for every substring of our input. If we have a longer word, we can once again chop it into pieces, and then for every pair so for every jump of length 1, we apply the same black box. And then for every jump of length 2, we apply the same black box. And then for every jump of the length 4 and for length 8 and so on. So we can now compute the same sketch for every subword. starting at an even position divisible by d, and we can achieve it in a total time n over epsilon. And in fact, so because I said at every position starting at position divisible by d, so we need to repeat the same step d times. So the total cost is d times n over epsilon. So this is a suboptimal n over epsilon cube. We can be a little bit smarter about this because computation on a pattern side for those L2 distances is n over epsilon. Computation on a text side is n over epsilon cube. So we can actually balance a little bit the work here. So we can compute more sketches on a pattern side, less sketches on a text side, and get n over epsilon squared time for both. So we can avoid computation of convolution for Euclidean distances. And now the observation is that, well, other norms kind of reduce to L2, but at a cost. So explicitly, if we have a Hamming norm and we have large alphabet, we can reduce it to binary Hamming by just doing some unary encoding, some positional encoding, but this blows up everything by a factor of the size of the alphabet. And then the binary Hamming is the same as L2. On binary words, every norm is the same. So doing it explicitly introduces a cost of size of the alphabet, but we can actually do it implicitly because after this step, after the reduction from Hamming to binary Hamming, the words are sparse. So this can be reduced to a simple hashing procedure. And for L1, if we have a natural number as an input, well, we can reduce it to binary Hamming by writing consecutive ones. And then it still coincides with L2. And this can be, with some extra preprocessing, also done, not explicitly, but implicitly. I will maybe not discuss the technical details here, but after doing all of this, we cannot do this rebalancing step that we did for L2, so we just have to pay the full price of n over epsilon cube. But we can fully avoid computation of convolution. So the takeaway here is that, well, we can do 1 plus minus epsilon approximation of L2 distances and for Hamming and L1 distances just by using basic bit arithmetic. So it will be addition, subtraction, and a multiplication and division by 2. I mean, of course, at the end, if you want a true L2 distances, you need to apply square root somewhere and so on. But I mean, let's forget about this little technical detail. If we compare to what can be achieved using FFT, where L2 distances can be computed exactly in n log n, and 1 plus minus epsilon approximation of Hamming and L1 distances can be done in time n over epsilon. So we are not improving state of the art. We are just saying, well, it's more about new techniques and adding more techniques to the bunch of existing, hoping that it will produce some improvements. Maybe someone will just have a brilliant idea how to use it. Question is, can it be applied to other norms? can it be done faster? Can it be applied to streaming? There are many open questions here. Thank you.
Thanks a lot.